March 15, 1942, off the coast of New Jersey. The black ocean surface split open, briefly illuminated by the flash of a torpedo striking steel plate, sing another lifeline of Allied material to the bottom of the Atlantic. This was the opening act of Operation Paukenschlag, or Operation Drumbeat, and the United States was utterly unprepared for the silent, sustained assault on its own coastline. German U-boat commanders had discovered a target-rich environment unlike anything they had encountered since 1939. American coastal cities were still blazing with light, providing perfect silhouettes for Allied vessels. Tankers, freighters, and troop carriers sailed predictable paths, and the U.S. Navy lacked the destroyers and intelligence necessary to protect them. In the first 6 months of 1942 alone, German U-boats sank over 500 ships in the North Atlantic, a slaughter so efficient that the submariners called it the happy time. This relentless destruction translated into a mathematical problem known as the tonnage war. Simply put, we had to build ships faster than the Germans could sink them, or the war would be lost before a single American soldier could fire a shot in Europe. Every sinking meant the loss of desperately needed oil, aluminum, steel, and food destined for Britain, which was hanging on by a thread. But traditional, established shipbuilding methods made matching the pace of destruction impossible. Shipbuilding, prior to the war, was an ancient, precise craft, demanding immense patience and skill. The standard method for constructing a large, seaworthy vessel, a method dating back decades, was riveting. A modern freighter required perhaps 700,000 rivets, each applied by a skilled team of 4 or 5 men. This labor was not only intensive, but it locked the shipyard into a long, slow timeline, dictated by the inherent limits of the process. Before Pearl Harbor, it took approximately 8 months, over 230 working days, to construct a single large freighter from keel laying to launch. Even after the declaration of war, when yards began instituting multiple shifts and aggressive schedules, the traditional process could only be compressed so much, typically yielding a new ship every 6 months. Maritime administrators calculated that in 1942 alone, they needed to replace 8 million tons of lost shipping capacity just to keep supplies steady. Yet, relying on the existing infrastructure and the centuries-old techniques of riveting, the best projections suggested they could deliver only 2 million tons. When U-boats were sinking 4 ships a day, waiting 6 months for one replacement guaranteed absolute failure. The shipyard was fundamentally constrained by geography and specialized labor. Everything had to happen in sequence on the slipway. The keel laid, the frames attached, the plates riveted. If one team was delayed, the entire construction line froze. If skilled riveters were unavailable, the hull sat unfinished. The traditional system was rigid, slow, and reliant on a vanishingly small pool of highly trained artisans who could not be manufactured overnight. The government recognized that they could not win the tonnage war by simply running faster. They needed to cheat time itself. They needed a process that treated the ship not as a massive, unique, artisanal project constructed sequentially from nose to stern, but as a giant, disposable toy built from interchangeable parts. They needed to move the complex labor away from the bottlenecks of the slipway and into the vast, open, easily accessible factory floor. They needed to break every rule of naval architecture, and for that, they had to turn to a civilian who had never built a single ship in his life. January 1st, 1941, 9 a.m. at the U.S. Maritime Commission headquarters in Washington, D.C. The problem staring down the aging admirals was not simply manpower or steel, but physics. The entire weight of maritime tradition dictated that building a freighter was a gargantuan, sequential undertaking, requiring the ship to remain fixed on the slipway for nearly 8 months. That 230-day production cycle was not arbitrary. It was the consequence of the tools and the methodology they were unwilling, or perhaps unable, to discard. The slipway, that long, slanted ramp that ed in the water, was the single most valuable, most congested, and most dangerous piece of real estate in any shipyard. Once the keel was laid on that narrow track, the entire project became a construction traffic jam. Hundreds of specialized tradesmen, fitters, chippers, caulkers, and, above all, The riveters had to swarm the hull simultaneously, working vertically and horizontally, often dangling from makeshift scaffolding high above the frozen ground or baking metal plates. The traditional steel plates of the hull were not welded together, they were hammered. Riveting was the primary bottleneck, a specialized ballet of noise and coordination that consumed immense stretches of time. For every single rivet, and a large cargo ship required 500,000 of them, a 4-man team was needed. One man heated the rivet until it was cherry red, another tossed it perfectly across the void. A third held a heavy bucking bar against the rivet head on the inside of the hull, and the fourth, the riveter, smashed the opposite side flat with a deafening, vibrating pneumatic hammer. This process had to occur hundreds of thousands of times, often in dark, cramped, greasy spaces deep within the structure. The crews were working in close proximity, constantly blocking each other's access to the hull. If the heaters were slow, the riveters waited. If the fitters misaligned a plate, the entire section of the ship was delayed. Because the work was confined to the boundaries of the slipway, no new major piece could be fully completed or moved into place until the preceding piece was securely fixed and signed off. This absolute sequential deepness meant that the production curve was shallow and long, stretching out the time and multiplying the logistical headaches into months. The ship grew slowly, like a pearl in an oyster, one layer at a time. The work environment on the slipway was inherently inefficient because the specialized labor, the best engineers, the master carpenters, the precise measurers, were tied up performing complex, finicky tasks in the least accessible location. The slipway was not a workplace. It was a bottleneck designed by 2 centuries of shipbuilding history, consuming the better part of a year for every single hull built. To defeat the U-boats, America needed hundreds of ships faster than the enemy could sink them, and the existing capacity was catastrophic. They were running up against simple mathematics. If the Allies could only produce ships on a 230-day cycle, the war effort was doomed. This meant they had to reject the fundamental principle of sequential construction entirely. They had to free the workforce from the tyranny of the ramp and remove the most difficult tasks from the congested space of the slipway. They had to take the shipyard, which had always functioned like a small medieval village of skilled sequential craftsmen, and redesign it from the ground up to act like a modern, continuous assembly line. This meant adopting revolutionary concepts like modular construction and, crucially, embracing a joining technique the old guard despised as unsound and risky: arc welding. This was the core challenge that faced the ambitious, rule-breaking civilian who saw the 230-day construction schedule not as a maritime inevitability, but as an engineering puzzle waiting to be broken into thousands of manageable pieces. December 20th, 1940, in the dusty, undeveloped flats near Richmond, California, the man known as the ambitious, rule-breaking civilian was introduced to the skeptical world of naval construction. This was Henry J. Sess's Kaiser, a man who, ironically, had never built a single ship in his life. His expertise lay not in the sea, but in concrete and earth-moving. Kaiser was the titan who had wrangled the Hoover Dam and the Grand Coulee Dam into monumental existence. He saw ships the way he saw poured cement and structural steel, not as unique nautical artifacts crafted by masters, but as enormous, repeating industrial products. He looked at the traditional shipyards where crews meticulously built the entire vessel piece by agonizing piece directly on the slipway and saw catastrophic, time-wasting inefficiency. The traditional process was artisanal, slow, and relied entirely on a highly specialized, unionized workforce that America simply did not possess in the volume required for total war. Kaiser sought to replace the artisan with the assembly line worker, introducing the revolutionary concept of parallel production to the maritime world. He didn't just embrace modularity, he perfected it, insisting that 80 to 90% of the entire ship be constructed far from the slipway. Sections weighing up to 200 tons, the double bottom, the deep tanks, the entire deck houses, were fabricated simultaneously in vast indoor workshops by newly trained crews. This parallel staging was the critical shift that unlocked unheard-of speed. If you could build every complex piece outside the choke point of the slipway, The final assembly became nothing more than a giant, specialized fitting operation. This strategy was why arc welding became absolutely indispensable. Riveting took days, created noise pollution, and required precise, specialized fitting by skilled workers. Arc welding, though initially controversial for structural strength, was fast and, crucially, could be taught in a matter of hours to any capable individual, regardless of their prior experience or genre. Kaiser didn't just accept unskilled labor, he banked on it. He hired women, retirees, farmers, and men previously disqualified by the established union yards, setting up rapid training schools on site to turn them into specialized welders and fitters in weeks. His shipyards operated 24 hours a day, fueled by multiple shifts, treating the raw materials steel plate-like iron dough being constantly extruded into standardized repetitive loaves. This simultaneous construction was the core of Kaiser's trick. Instead of tying up a single precious slipway for 230 days while fitters waited for plate and welders waited for fitters, his yards reduced the time on the slipway itself, the final assembly area, to mere weeks, sometimes only days, before the next hulking piece was rolled into place. The slipway was no longer the construction site, it was merely the final jig. This was mass production on a scale never before imagined for something so immense, a perfect marriage of Fordism and maritime necessity, designed to overwhelm the Axis not with better vessels, but with sheer unimaginable volume. January 29, 1945, 2 p.m., at the Oregon Shipbuilding Corporation facilities. The key to accelerating construction lay in eliminating the traditional constraints of the shipyard. Instead of painstakingly building the entire 441-foot ship piece by piece, where every worker relied on the preceding task being finished, the Liberty vessel was intellectually dismantled into roughly 250 massive, standardized sections. These sections, some weighing over 100 tons, were built simultaneously in massive indoor sheds, protected from the elements, using factory floor techniques. The ship was no longer a single organism, it was a gigantic industrial mechano set. This modularity required total standardization. Every plate, every bulkhead, every mast footing had to be exactly identical across all 17 emergency shipyards operating under the program. It was a massive undertaking in industrial organization, ensuring that the parts built in Richmond, California would fit perfectly onto a keel laid in Portland, Oregon. This interchangeability was the true revolution. The other radical shift was the wholesale adoption of electric arc welding over traditional riveting. Riveting was a specialized, deafening, and slow process, requiring teams of 4 skilled tradesmen to heat, toss, catch, and hammer thousands of rivets into place. Welding, while demanding, allowed the work to be broken down into simpler, repeatable tasks. It required less initial skill and, critically, it was quieter, allowing supervisors to communicate more effectively in the bustling yards. And these welding torches were not wielded by the typical highly experienced shipyard journeymen of old. To meet the astronomical demand for labor, shipyards had to tap into entirely new demographics. Suddenly, the ranks of American industry swelled with women, the iconic Rosie the Riveter, as well as formerly marginalized workers, African Americans and others, who had previously been excluded from specialized trade unions. They were trained rapidly, focusing on specific welding seams or installing predetermined pipes, contributing to the incredible pace of assembly. This simplification of labor and standardization of components allowed for the truly astonishing bottleneck breaker, the 3-shift, 24-hour workday. With components flooding out of the fabrication sheds constantly, the slipway received a non-stop flow of parts. Gigantic cranes, some capable of lifting 300 tons, plucked these prefabricated double-bottom sections, bow pieces, and superstructure blocks and dropped them into place with terrifying efficiency. What once took months to complete now happened in less than a week. The pace became a competitive frenzy between the yards. The world watched in disbelief as Henry J. Kaiser's yards pushed production past the 30-day mark, then the 20-day mark, and finally the unthinkable was achieved. On November 12, 1942, the SS Robert E. Peary was launched a mere 4 days and 15 hours after its keel had been laid. 4 days. The traditional construction cycle had been shattered and redefined. The Axis strategy of sinking ships faster than the Allies could build them had officially failed. The scale of American industrial power had been weaponized. It was an overwhelming, unending flood of cargo space aimed directly at the U-boat menace. That overwhelming, unending flood of cargo space was not conjured by magic or simply by adding more hammers. It was the direct result of a technological revolution implemented with ruthless efficiency, the electric arc weld. For generations, the backbone of any large steel structure, particularly a ship, had been the rivet. Shipbuilding was a heavy, specialized craft that demanded precision alignment. To build a ship, the traditional way meant drilling hundreds of thousands of holes and seeing teams of heaters and catchers and buckers and pounders to secure close to 600,000 hot steel pins through overlapping plates. The work was deafening, dirty, and dangerous, and most importantly, it was incredibly slow. Riveting demanded that the ship stay whole and intact on the slipway for the entire duration of its construction, tying up the most valuable piece of real estate in the yard for 4 to 6 months. This constraint was the fundamental barrier to speed. Riveting did not allow for the decentralization of labor, but the new method, electric welding, changed the physics of the shipyard forever. Instead of painstakingly joining overlapping steel plates with individual rivets, welding fused the metal into a continuous, seamless joint. This simple shift in technique had extraordinary downstream consequences. The maritime old guard engineers trained in the rigid strength of riveted plates were deeply skeptical of this new, seemingly delicate fusing method. They worried about brittleness, about the unseen stresses created by the heat, and about the quality control of a technique that was easy to learn but difficult to master flawlessly. But the necessity of war overruled these traditional fears. Welding was the indispensable key to the true revolution. Prefabrication. If you could weld components together, you no longer needed to build the entire ship structure in one location. You could break the ship down into hundreds of smaller, manageable sections. This meant that the steel mill, the machine shop, the pipe fitters, and the electricians could work simultaneously hundreds of yards away from the main building berth, fabricating massive blocks of the ship in parallel. These were not small pieces. Cranes were soon lifting 30-ton deck sections, full bow assemblies, and complex self-contained engine room modules into place. These huge pre-welded pieces were built upside down, right side up, or sideways, allowing workers complete flat access to their jobs, eliminating the dangerous and slow work of scaffolding high above the ground. The laying of the keel on the slipway, the ceremonial starting point of shipbuilding, was no longer the beginning of construction. It was merely the start of the final assembly. The slipway, which used to be occupied for half a year, became a temporary staging area. Instead of weeks of intensive, continuous work, the massive gantry cranes simply positioned the pre-made blocks like gigantic interlocking components. The skilled men on the slipway were then responsible only for the final critical fusion welds that joined these massive blocks together. This system allowed Henry Kaiser and the men who embraced his vision to turn ship assembly into what was essentially a massive industrial production line. The sheer volume of labor of men and women wielding welding torches in hundreds of separate indoor shops was channeled directly into preparing the parts needed for the next ship in line. By the time the keel was laid, as much as 75% of the physical work was already complete and waiting. The time on the slipway dropped not merely from 6 months to 6 weeks, but ultimately, incredibly, to those stunning 4 days and 15 hours. That speed was achievable because the ship did not have to be built, it only had to be put together. The rivet had been supplanted, and with it, the constraints of time and space had finally been overcome. July 10, 1942, 6 a.m. at the Oregon Shipbuilding Corporation yards in Portland. This newfound freedom from traditional constraints demanded a complete overhaul of the physical infrastructure supporting the work, turning the traditional shipyard into a gigantic, meticulously choreographed assembly stage. The concept was simple. If the ship was now a collection of pre-made parts, then the factory that built those parts must stretch far beyond the muddy banks of the Willamette or the Potomac. The factory became invisible, sprawling across the continent. To achieve 4-day construction times, every single component had to arrive at the precise moment it was needed, exactly as specified, and perfectly interchangeable. This required a level of logistical coordination never before attempted in American heavy industry. The massive steel plates, which once sat stacked high next to the berths waiting to be painstakingly marked and rolled by local labor, were now cut, shaped, and welded into sections weighing tens of tons, hundreds of miles inland. Boiler systems came from the industrial shops of Pennsylvania. Deckhouses, complete with wiring and plumbing already installed, traveled by rail car from Chicago. Engines built for mass production were standardized in Wisconsin. The standardization inherent in the Liberty ship design, all 10,000 tons of it, was the skeleton key that unlocked this logistical engine. Because every ship was identical, suppliers across the nation did not need custom orders for every single hull number. They produced thousands of standardized bulkhead sections, bow pieces, and rudder assemblies, knowing they would fit any hull under construction in any yard, from Richmond, California, to Mobile, Alabama. This was the true genius of the system. It didn't just speed up work on the coast. It leveraged the entirety of America's industrial capacity simultaneously. On the local scale, the layout of the shipyard itself had to be radically altered. Traditional yards were focused on the single long slipway, a linear operation where raw material entered one and slowly migrated toward the finished ship. The new modular system demanded flow. Yards were redesigned into vast horizontal staging areas. Adjacent to the assembly lines were immense fabrication bays, often covering acres of ground, where small subassemblies, the double bottoms, the side shell panels, were fused into large multi-ton chunks known as subsections before ever approaching the water. These staging areas became the nexus of the operation, demanding enormous power and unprecedented material handling capability. If a hull section weighed 60 tons, the infrastructure needed to move it safely and efficiently. This gave rise to the iconic, huge gantry cranes, towering monsters that dominated the coastal skyline. These cranes, capable of lifting 100-ton sections and swinging them with precision over multiple berths, were the muscle of the invisible factory. They replaced hundreds of small teams of workers painstakingly aligning plates and bolts. A crane could deliver an entire mid-ship section, dropping it into place where welders were waiting to fuse it to the adjoining module, turning weeks of work into a matter of hours. Furthermore, the entire environment had to be optimized for the new workforce. The old, dusty, and dangerous yards were replaced with massive, well-lit welding sheds and organized staging areas, allowing work to continue around the clock in all weather conditions. Since the majority of the welding and preparatory work was no longer performed high up on the unstable hull but down on ground level, safety improved and quality control became far easier. Inspectors could walk along the ground, checking massive seams before the piece was lifted into place, ensuring the integrity of the crucial welds that held the entire ship together. This shift meant that when a ship finally sat on the ways, the only activities required were the large-scale choreography of lifting, aligning, and final joining. The hull, which had taken 6 months to construct section by section, was now assembled like a giant metal jigsaw puzzle in under 4 days, demonstrating that the genius of American mass production, honed on automobiles and appliances, could be applied with shocking speed to the most complex machine yet devised, the ocean-going freighter. October 10, 1942, at the Oregon Shipbuilding Corporation in Portland, the sheer mathematical implication of the 4-day hull assembly model became the greatest crisis of manpower America had ever faced. If Henry J. Hall, Kaiser's yards, and the dozens that followed his lead were going to launch 3 ships a week instead of 3 ships a year, they needed not just new designs, but a new army. The genius of prefabrication had eliminated the bottlenecks in engineering and staging, but it had created a monstrous vacuum in skilled labor. Each Liberty ship, even in its simplified design, still required 30,000 major welds, 3 miles of piping, and the installation of over 200,000 separate components. The United States was suddenly demanding hundreds of thousands of certified shipwrights, welders, pipefitters, and crane operators simultaneously, while the traditional pool of young, experienced men was rapidly shrinking into the uniform of the United States military. The solution to this impossible demand mirrored the solution to the impossible schedule: standardized, simplified mass production applied not to steel plates but to human skills. Shipyard training schools sprang up faster than the mess halls, where once a master shipwright spent 3 to 5 years taking an apprentice under his wing. The Kaiser yards developed intensive proprietary training programs measured in weeks. They realized that in the age of prefabrication, a worker did not need to know the entire process of building a ship. They only needed to know one highly specialized operation perfectly. The vast, complex task of maritime construction was broken down into hundreds of simple, repeatable steps. Welders learned only the basic downhand technique required for assembly line steel plate joining. Electricians learned to run specific wiring looms according to color-coded schematics. In many cases, the only prerequisite for these high-speed courses was the ability to hold a specific tool and follow a precise instruction. This radical simplification of labor threw open the doors to the last great untapped industrial resource in the country: the women of America. Suddenly, shipbuilding was no longer the exclusive domain of muscular men raised on the docks. Women streamed into the yards from farms, offices, and kitchens, drawn by patriotic fervor and, crucially, by wages unheard of for female employment in prior decades. In a few months, women comprised 25% of the total workforce in American shipyards. They proved remarkably adept at the focused, repetitive nature of mass production work. They excelled at welding, often preferred for their steady hand and smaller stature, which allowed them to maneuver better in the constricted interior sections of the hulls. They learned to run overhead gantry cranes, guiding multi-ton sections of deck and superstructure with deft precision, and they quickly mastered layout, rigging, and painting. The myth of Rosie the Riveter, the iconic symbol of this wartime mobilization, was not merely propaganda. It was the documented industrial reality of how America created a skilled workforce of over 2 million people almost literally overnight, allowing the shipyard production schedules to keep pace with the frantic demands of the Atlantic and Pacific theaters. The human element, just like the structural engineering, was now being fabricated at maximum speed. Despite the triumph of organizational logistics, the speed of production became its own immediate enemy. The old guard, the seasoned veterans of traditional shipbuilding, viewed the spectacle of a hull being welded together in sections like colossal, misplaced pieces of a jigsaw puzzle with deep, fundamental skepticism. They knew ships took time. They knew the sea respected neither schedule nor novelty. The traditional method, relying on millions of rivets, ensured that if stress occurred, the plates would merely leak, giving the crew time to respond. But welding created a monolithic structure, seamless and rigid. The skepticism was not merely philosophical. It was validated by terrifying incident reports starting in the brutal winter of 1942. As the Liberty ships sailed through the icy waters of the North Atlantic, the stress of heavy seas combined with the extreme cold revealed a flaw inherent in the design's transition from old methods to new. The phenomenon was catastrophic brittle fracture. A crack that might have stopped at a riveted joint in an older vessel could now travel unhindered through the continuous welded seams of a Liberty ship, racing across the hull plates at incredible speeds. The ships were, in essence, splitting themselves in half. The failure was rarely gradual. It often started, ironically, at the sharp corners of cargo hatches or along the sheer strake-the-joint between the side plating and the main deck areas, where stress concentration was highest. One moment, the ship was traversing the swell. The next, the structure failed completely, the two halves diverging with terrifying finality. This was not a minor inconvenience. It was an existential threat to the entire Allied war effort. If the vessels carrying the essential supplies could not survive the voyage, the industrial miracle happening on the American coasts was meaningless. Suddenly, the focus shifted from sheer speed to critical structural integrity, forcing an emergency deep dive into the metallurgy and practice of wartime welding. The investigation, led by engineers and naval architects, quickly determined that the fault lay not necessarily in the concept of welding, but in the specific mass-produced execution of it under extreme time pressure coupled with the quality of the basic, low-grade rimmed steel plate being rapidly rolled out by the mills. This steel became fatally brittle when temperatures plummeted. The initial response was immediate and comprehensive. Every single shipyard had to pause and implement structural changes. Critical stress points, such as the infamous square hatch corners, were redesigned and retrofitted to be rounded, dispersing the strain. Welding procedures were rigorously scrutinized, requiring higher standards of inspection for the welding beads themselves, ensuring they were fully penetrating and free of voids. Crucially, some concessions were made to the traditional methods. To prevent cracks from traveling the entire length of the hull, engineers mandated the introduction of crack arresters, strategic lines of riveted plates or specialized higher quality welds that acted as barriers, preventing a fracture from propagating from one side of the ship to the other. This systematic adaptation was the final and most crucial evolution of the Liberty Ship program. It proved that the system could not only build ships faster than anyone believed possible, but that it could also quickly learn and self-correct fatal flaws while maintaining an unbelievable production schedule. The yards were no longer merely assembling hulls. They were perfecting a radical new form of industrial fabrication, balancing the necessity of 4-day construction against the absolute demand for wartime reliability. The successful refinement of the Liberty ship design under this duress meant that the final ships produced were structurally superior and far more reliable than the initial ill-fated runs. The logistical revolution had survived the test of the ocean. January 1st, 1942, at the Oregon Shipbuilding Corporation Yard, Portland. The blueprints had been proven. The seams held. The sea trials confirmed the radical method of welding and sectional assembly was sound. The logistical revolution had passed its structural exam, but now it faced the real-world clock of the Battle of the Atlantic. The initial Liberty ships, those first successful attempts, still required an average of 105 days from the laying of the keel plate to the ship's launch. 105 days was already a miracle compared to the 9 months traditionally required for a riveted freighter. Yet, against the backdrop of staggering losses inflicted by German U-boats, 105 days felt like a lifetime. The directive from Washington, filtered down through the Maritime Commission, was succinct and brutal. Drastically cut the schedule, or the entire LEs and logistical pipeline to Britain and the Soviet Union would collapse. The civilian industrialists who championed this revolution understood that fear and patriotism were powerful motivators, but competition and sheer, impossible audacity were even better. He needed a number that broke the psychological barrier of traditional craft shipbuilding. The initial goal, therefore, was simple: slash the production time in half again. The first major proof of concept came not from engineering genius, but from managerial ruthlessness and spatial reorganization. Why were ships taking 100 days? Because the assembly process was still bottlenecked at the slipways. If one crew was slowed waiting for a crane, every subsequent step stalled. The solution was the further expansion of prefabrication. Sections that had previously been welded near the slipway were moved into enormous assembly sheds, often miles away from the water. These sheds became gigantic production floors where unskilled workers, women and men trained in highly specific tasks, could weld in predictable, flat environments, unimpeded by weather or the complexity of working on a curving hull high above the ground. By February, using optimized assembly jigs and the first implementation of truly monumental cranes designed specifically to lift 60-ton sections, the yard managed to turn out a ship in 90 days. Then, 85. The race had begun, not against the enemy, but against the timer hanging on the yard foreman's office wall. The true breakthrough arrived when the shipbuilding process was formalized into a 50-day metric. Hitting 50 days meant eliminating nearly 80% of the time required by traditional methods, and nearly half the time needed by the initial experimental welded design. The key was synchronicity. Every yard worker, whether running a welding torch or operating a massive overhead gantry, was part of a tightly choreographed ballet. If the number 5 bulkhead was supposed to arrive at the keel at 2 a.m., Tuesday it arrived at 2 a.m. Tuesday, or the entire sequence failed. This relentless adherence to the schedule was the true genius of the civilian system. It didn't rely on master shipwrights, of which America had very few. It relied on absolute repeatability by people who had been driving tractors or working cash registers just weeks before. The complexity was transferred entirely from the ship itself to the logistical planning matrix. The average production time for the Kaiser yards dropped from 80 days down to 60 in the spring of 1942, and then, fueled by patriotic drive and incentive bonuses, fell straight through the floor. As summer approached, the goal was no longer merely having the time. It was pushing the boundaries of physical possibility. If a ship could be built in 40 days, why not 30? If 30, why not 20? Shipbuilders, the few remaining traditionalists, watched in horrified awe as massive sections of steel that had once taken weeks to align were simply dropped into place like oversized Lego blocks. The final constraint was no longer welding time, but the time it took for the hull to dry and for the machinery to be fully bolted and connected below deck. The concept was no longer proving that modular construction worked. It was proving how fast humans could physically assemble the modules. By the time the initial trials were complete, the average build time across the key production yards hovered around 42 days. It was an astonishing reversal of industrial logic, transforming the year-long undertaking into a 6-week project. But the most ambitious phase of the campaign, the ultimate ridiculous claim that defined the war effort, was yet to begin. The civilian had set the bar not at 42 days, but at 4. To achieve that impossible benchmark required not just streamlining the process, but breaking the rules of the Kalar itself. To achieve that impossible benchmark required not just streamlining the process, but breaking the rules of the Kalar itself. The experiment, publicly derided as a publicity stunt that risked catastrophe, would center on hull number 440, soon to be christened the SS Robert E. Peary, built at the vast Kaiser shipyards in Richmond, California. The prevailing method, even in the optimized 6-week schedule, still demanded linear assembly. The keel was laid, ribs were set, plates were welded, and only then could the engine room be fitted, followed by the superstructure. The 4-day plan demanded that nearly 80% of the ship be built off the ways, simultaneous construction miles apart, converging on a single moment. The civilian's genius lay in demanding that workers stop thinking of the ship as a single monolithic project and start seeing it as 50 massive, prefabricated modules. While the keel blocks were still being set on the slipway, entire deck houses, complete with plumbing, wiring, beds, and even fresh coats of paint, were being hoisted onto flatbed rail cars. Engine rooms, meticulously wired and ready for steam connections, were prepared in the machinery shops long before the hull plates they would sit within were even rolled. The yard became a monstrous clockwork mechanism where every move was choreographed down to the minute, eliminating any downtime where one trade waited for another to finish. The official timeline began on the morning of November 8, 1942. The sound that emanated from Richmond was less the familiar clang of welding and more the roar of relentless mechanized ambition. 3 shifts merged into a single sleep-deprived entity. Floodlights turned night into a perpetual harsh twilight. The speed was terrifying. The 60-ton sections that made up the forward hull were dropped into place one after another, like children stacking blocks. Except these blocks needed perfect alignment for the high-speed welders who swarmed the structure. By the end of the first day, 25% of the hull was assembled, a feat that previously took 12 weeks. As day 2 began, the massive 12-story tall cranes were continually hauling colossal subassemblies. The largest lifts were reserved for the central engine and boiler units, Pripeat modules weighing hundreds of tons, fitted into the precise cavity of the midship section. This was the moment of highest risk. If the alignment was off by even a fraction of an inch, the entire 4-day schedule would collapse into days of corrective labor. But the modular strategy paid off. The section slid home with unnerving precision. Day 3 was dedicated entirely to fitting out and finishing. Hundreds of workers flooded the interior, connecting the pre-installed wiring harnesses and running the final lengths of pipe. Plumbers, electricians, and carpenters worked in a terrifying, cramped ballet, driven by whistles and bullhorns that dictated when they had to clear a section for the next crew. They worked 24 hours straight to ensure that when the ship left the ways, it was not merely a hull, but a truly functional vessel. As the sun rose on November 12th, the fourth day, observers including skeptical Navy officials and reporters stood agog. Hull 440. The SS Robert E. Peary stood fully assembled on the ways, a colossal, functional ship where 4 days prior there had only been a vacant foundation. The overall assembly time from keel laying to structural completion was an unbelievable 4 days and 15 hours. But the trick was not just assembly. The ship had to be launched. At precisely 11:30 a.m. on that Thursday morning, the final blocks were knocked away. The hull, glistening under its fresh coat of gray wartime paint, slid smoothly down the ways and splashed into the tidal waters of the San Francisco Bay, met not with polite applause, but with a roar of disbelief and triumph from the exhausted shipyard workers. The old world of shipbuilding, where a Liberty ship took 230 days, had been vanquished not by a technological breakthrough, but by a radical overhaul of human organization. The civilian had demonstrated the impossible. Not only could a ship be built in 4 days, but the principles used to achieve it could now be applied to the wider shipbuilding campaign. The SS Robert E. Peary became the paradigm, forcing every other shipyard in the nation to instantly recalibrate their expectations. If Richmond could do it, so could they. The average build time plummeted from 230 days to 56 days almost overnight. The impossible trick had now become the industrial standard, ensuring that America's capacity to build eclipsed Germany's capacity to sink. The relentless punishing effort of those 4 days provided the crucial logistical edge the Allies desperately needed to flood the Atlantic and Pacific theaters with the material of war. November 19, 1942, aboard U-515 prowling the West African coast, the tactical reality began to shift against Admiral Jernitz's wolf packs. The U-boat crews were still highly successful, sinking Allied tonnage at alarming rates, but the underlying arithmetic of the war had changed fundamentally. Previously, the equation had been simple and grim for the Allies. Germany could build U-boats faster than Britain could replace lost merchant ships, and certainly faster than the United States was capable of building ships from scratch. Every successful torpedo hit represented a permanent logistical wound, but the new standard of production, the miraculous output that guaranteed a new Liberty ship entering service every 4 days, did not merely reduce the deficit, it reversed it into an insurmountable surplus. The flow of steel and machinery from American yards was no longer a trickle to be contained, but a tidal wave that threatened to drown the entire German naval strategy. Jernitz's strategy relied on the crippling psychological and economic effects of sinking ships. The resulting shortage was supposed to choke Britain into submission and prevent the necessary American buildup for a second front. When the average build time of a critical vessel dropped from 7 months to less than 7 weeks, the foundation of this strategy crumbled. The tactical implications were immediate and brutal for the U-boat fleet. Allied planners could now afford to take risks, running convoys that were previously deemed too large or too poorly protected. Convoys swelled in size. Before the war, a merchant convoy might number 20 or 30 ships. Now the huge mid-Atlantic formations swelled to 70, 80, even 90 vessels, a traffic jam of vital supplies stretching across miles of ocean. When a U-boat captain sighted such a sprawling target, the challenge was overwhelming. Torpedo capacity was limited, typically to 20 or 22 rounds. Even a perfect attack sequence resulting in 5 or 6 sinkings was now merely a pinprick against a fleet of nearly 100 ships. The remaining 90-plus ships, loaded with tanks, ammunition, aviation fuel, and creations, continued on their course to Britain or North Africa, virtually guaranteeing that the strategic delivery goal was met. The loss ratio, once devastating, became manageable. The sheer proliferation of available tonnage also allowed the Allies to execute the necessary maneuvers to defeat the U-boats themselves. With America no longer desperately hoarding every available escort vessel to protect irreplaceable existing merchant ships, resources could be diverted. Escort carriers could be released from convoy duty and deployed for aggressive hunter-killer operations. Long-range patrol bombers, now based on islands, stocked and supplied by these constant stream of Liberty ships, patrolled the infamous Atlantic Gap with increasing impunity. The ships themselves, while slow and unglamorous, became strategic decoys. Their overwhelming numbers forced U-boats to reveal their positions, drawing out the wolf packs and exposing them to advanced Allied detection technologies like high-frequency direction finding, HF-DF or Huff-Duff, and powerful radar. The U-boats were constantly hunting, which meant they were constantly being hunted in turn. By early 1943, the rate of Liberty ship launchings significantly exceeded the rate of sinkings. The United States was completing 100 ships in the time it took the U-boats to sink 60. The logistical reserves of the Allies were not merely being maintained, they were expanding exponentially. This accumulation meant that when the decisive battles of the Atlantic occurred, culminating in the disastrous German losses of Black May 1943, the Allies had the operational flexibility to absorb huge losses while simultaneously deploying overwhelming force to eliminate the U-boat threat entirely. The material of war supplied by these rapidly built hulls enabled Operation Torch, the invasion of North Africa. They ensured the survival of Britain through the worst years of the war. Most critically, the constant, reliable stream of material established the necessary logistical backbone for the invasion of Fortress Europe. Every tank landed on Omaha Beach, every gallon of gasoline poured into Patton's advancing columns, and every railway tie used to rebuild the destroyed infrastructure of France owed its passage to the unprecedented output of American civilian shipyards. The ultimate measure of the impossible trick performed by American labor and ingenuity was not just the speed of construction, but the strategic certainty it provided the Allied High Command. No matter what the Germans sank, the replacements were already on the slipways rolling down the assembly lines or waiting just over the horizon. The relentless, punishing effort of those 4-day construction cycles had provided the Allies with the war-winning logistical superiority, transforming the sea lane from a killing ground into a secure supply route. The relentless, punishing effort of those 4-day construction cycles had provided the Allies with the war-winning logistical superiority, transforming the sea lane from a killing ground into a secure supply route. When the last German U-boat was sunk and the final Japanese sower signed, the American shipbuilding miracle did not simply cease, it morphed. Henry J. Kaiser had created not just ships, but the template for modern heavy industry. The assembly lines, the vast, specialized yards, and the workforce skilled in rapid sub-assembly fabrication all were assets too valuable to discard. The principle that had made the Liberty ship possible, the industrial conviction that massive projects could be broken down into repeatable, easily managed modular pieces built far from the main assembly point, was now ready to reshape the American civilian landscape. Kaiser's method, the very trick that reduced years to days, transitioned seamlessly from military logistics to peacetime commerce. The sheer scale and efficiency he pioneered became the standard for American post-war construction and manufacturing. Kaiser applied the same high-speed, prefab mentality to infrastructure projects. Dams, bridges, factories, and entire planned communities benefited from the industrial logic forged under the pressure of wartime necessity. He plunged into the housing market, creating affordable, prefabricated homes using the same assembly line efficiency that once birthed the SSS Patrick Henry. He was the first industrialist to truly leverage aluminum in mass quantities, recognizing the potential of the metal that wartime necessity had forced into production. Kaiser Aluminum became a behemoth, driven by the same organizational efficiency that had defined his shipyards. Even more boldly, Kaiser tackled the entrenched conservative automotive industry, applying his rapid prototype methodology to the creation of the Kaiser-Frazer automobile, aiming to deliver cars faster and more affordably than the established Detroit giants. Though the auto venture itself ultimately struggled against post-war market saturation, the attempt demonstrated the unstoppable energy and belief in industrial acceleration that defined his legacy. Perhaps the most enduring, and certainly the most humanitarian, aspect of Kaiser's peacetime continuation was born directly from the necessity of his wartime workforce. Faced with hundreds of thousands of workers arriving in remote locations, demanding continuous, high-speed production, Kaiser realized that absenteeism and sickness were the primary threats to the 4-day cycle. His solution was to provide medical care directly, in-house, for his workers and their families, a revolutionary concept at the time. This system, established to ensure continuous shipbuilding capacity, grew into Kaiser Permanente, fundamentally changing how millions of Americans access healthcare, proving that the commitment to organizational efficiency could extend far beyond steel and rivets into human wellness. Henry J. Kaiser, the civilian who taught the world that naval construction was not an artisan craft but a process of logistics management, did not just win the war through ships. He provided the industrial methodology for the subsequent half-century of American economic dominance. The speed, the scale, and the relentless belief in the impossible he demonstrated on the slipways Eward, transforming American industry from the way cars were built to how medicine was dispensed forever, marking the legacy of the man who, by mastering the assembly line, created more ships than the enemy could ever sink.